Alright, we have a loop of wire like this, sitting on XY axis, horizontal, and then Z axis is axis of the coil, like that. And there's a current going around like this. We want to find the magnetic field of this loop of current at this point, at the distance Z from the center, but along the axis of the loop. The same as what we did before, we take a small piece of this, and we call it dl, and dl will be in that direction of the current, right? And this piece creates a magnetic field at this point. Can you tell me which direction is the magnetic field? Now, this is your formula. U naught I dl plus r hat. R is in which direction? R is always from source point to the field point. So this is our R. Which way is it? Yeah, it's perpendicular to both this dl and this r, and in the direction of dl cross r hat, which is in that direction. I call it like this, right? This is dB. I can also do that mathematically like that, but I think if you put it in math, it will be more confusing than useful. So I'm not going to do that. All the x and y components cancel out as you move the L around. Only z components add up. So B at this point is equal to integral, actually the magnitude of B is equal to integral of dBz. Only the z components survive, so B will be Bz, which is sum of all the z components. And then, now we need to calculate dBz. And if you take this as angle theta, you see that it will be dB magnitude times cosine of theta. So it will be integral of dB magnitude times cosine of this theta angle. But what is the magnitude of dB? What is the angle between dl and r hat? dl is this way, r hat is this way, right? Can you see that what angle there is between them? The element piece is like this, right? Let's say the part that's right in here going to this, and then r is like this. The angle between them is 90 degrees, right? It's hard to see maybe to imagine, but it's all 90 degrees all around. dl and r hat. R hat is like this. dl is like that. It keeps 90 degrees. And so dl cross r hat has a magnitude that is dl. We found the direction, right? Direction is this. But the magnitude of it is dl times magnitude of r hat times sine of the angle between them, which is 1. The magnitude of r hat is 1. Sine of 90 is 1. It just becomes just dl. So dB becomes mu naught I dl over 4 pi r squared. R squared is this length squared. But how is r related to z and radius of this circle, if the radius is r? You see there's another 90 degree angle here. And it makes to be accurate. This is also right triangle. R squared is actually z squared plus r squared. All right, and then what is theta, cosine theta? If this is theta, which one of these angles in this right triangle, theta also? The bottom one or top one? Let me become. Now this angle is also theta because we have this side which is r perpendicular to dB, this side which is in the xy plane perpendicular to z. So this angle is also the same theta as we have up there. And then cosine theta will be r divided by this r. So it will be r, capital R, divided by square root of z squared plus r squared, which is this, r squared z squared. So now we're ready to put everything in there. In the integral becomes integral of dB, which is mu naught I dl over 4 pi times r squared, z squared plus r squared. Then multiply by cosine theta, which is r, divided by square root of z squared plus r squared. Right? That's dB times cosine theta. And now, as this element goes around, the loop, everything that's constant should go out. The integral. What's constant? Mu naught I r to 4 pi. Is that constant? Yes, that's constant. R constant? Yeah, everything is constant. So it becomes mu naught I r over 4 pi and z squared plus r squared. Again, this is 1/2, this is 1, becomes 3/2 integral dl. What is integral of dl? What is integral of dl? If you add all the little elements here. The circumference, which is 2 pi r, right? So you can write mu naught I. 2 cancel, but I want to put pi still here. Pi r squared over 2 pi. 2 cancels, 4 becomes 2. Z squared plus r squared to the 3/2. And that's the magnitude of magnetic field, and it is in the z direction, right? Because the other 2 components cancel out, only z components survive. Because we have only one component, dz is the same as the magnitude. Right? Now, what is this pi r squared? The area of the circle, right? If you multiply by I, what do you get? Area times the current. Remember the magnetic dipole moment of a loop of current. Magnetic dipole moment, mu, of the loop of current is I times pi r squared, or times the area. So if you write it in terms of mu, this will be B equal to mu naught. Mu divided by 2 pi z squared plus r squared to the 3/2. And mu is this. And now if you have more than one loop in the, more than one turn in your loop of current, and each one has a current I, if you have n turns, mu becomes n times bigger. It's like the current becomes n times bigger, right? But this still becomes mu, not mu. But this mu is this, in general, mu is ni area. If you have n turns, n times I times the area of the loop. So let me generalize that. If you have n turns, or n turns in the coil, like this coil that we have has many turns. If you put a current I in it, the current multiplies by that n, right? Because each loop creates the same current, and it's in the same direction. So this is magnetic field of a loop of current with mu being this value, number of loops times the current in each loop times the area of the loop. Now, usually we are interested in the distances that are much larger than r. If z is much larger than r, you see you can ignore r in the denominator. And in terms of magnetic moment, just ignore this. Z squared to the power 3/2 becomes mu naught over 2 pi z cubed. For z is much larger than r, you can ignore the r, so b becomes mu naught mu over 2 pi z cubed. This is magnetic field of a magnet with magnetic dipole moment, or the loop of current with magnetic dipole moment mu at distance z that's larger than the dimensions of the loop. And of course in the direction of the mu itself. Remember, mu is a vector that has this magnitude. Right? In the direction that you can get also from right-hand rule, putting your forefingers in the direction of current going around, and thumb shows the direction of the magnetic dipole moment. All right, this is magnetic field created by a loop of current or coil along the axis, along the symmetry axis. Remember, this is all along the symmetry axis. If you're off this axis, the value is not there. I mean, that formula doesn't work, only along the symmetry axis. If you put z equal to 0, what do you get? If you have a coil and you want to find magnetic field of the current through that at the center of the coil, you can put z equal to 0, right? If you put z equal to 0, what do you get? You get mu naught mu over 2 pi r cubed, right? But in that case, it is better to use this one, because r cubed and r squared cancel out, then you get easier result. So let's say for B field at the center of loop of current, you use this one and put z equal to 0. You get r squared, r cubed, r cancel, pi cancel, you get b equal to mu naught I over 2r. Compared to that result, you see for the wire is mu naught I over 2 pi r here. Here we have mu naught I over 2r. R is the radius of the loop.